So in the next series of videos, we're going to go over chapter 2.2 from the Lock 5 textbook. And this section is all about analyzing, looking at one quantitative variable, specifically the shape of distributions and then the center. We'll talk about that as we go through this. And just as a quick reminder, all of chapter 2 falls under the category of descriptive statistics. We're learning how to describe, visualize, summarize different data sets. All right, so in this section, we're going to go over visualization, looking at some examples of dot plot and histogram. We'll use those visualizations to talk about shape, whether distribution is symmetric or skewed, measures of center, looking at mean and median specifically, and then we're going to look at outliers and statistics that are resistance to outliers. But first, let's do a review question from the last section. Given a two-way table from chapter 2.1, what percentage of patients survived? What percentage of patients who survived received pericalcitol? All right, now challenge you to pause really quickly and see if you can get the correct answer. And the correct answer is 53%. And I love giving these two-way tables on quizzes and exams because this is a conditional probability question. But if you don't see that, but you notice that we're looking at what percentage of patients who survived. So we're only looking at the survived column, which is why the denominator is 36,917. And out of all those who survived, how many received the pericalcitol supplement? And that's the 19,665. So take this ratio to get the 53%. Okay, so we're going to look at a lot of examples today centered around Hollywood movies in 2011. So we've got a bunch of data sets we're going to look at later on for box office gross and a couple on Rotten Tomatoes audience score. So this is from 2011, and just a note right here, we're going to look at some outliers in the top box office. This is worldwide box office that year was a Harry Potter movie. It had 1.3 billion box office, and then Transformers, Pirates of the Caribbean, and so on. And don't forget, we're going to categorize or organize data in terms of kind of a spreadsheet scenario where each column is a variable. So we've got the studio's variable, Rotten Tomato score, theater openings, genre, etc. And then each row is a case. In this case, each row is a movie. So a dot plot is a graph where each case is represented by dots, and the dots are stacked up. And probably the easiest way to see each case, we're looking right here at box office. So the box office, if you remember from the previous slide, is up here. The top box office is Harry Potter, I think, in the Deathly Hallows. And then the next two was Pirates of the Caribbean and Transformers. I forget which order they are as the top three grossing. But if you notice, most movies are centered around here. That made one made nothing, or made less than $100 million at the worldwide box office. Similar to a dot plot is a histogram. So the height of each bar corresponds to the number of cases within that range of variables. So the bulk of movies, this would be over 100, 120 or so movies earned between $0 and $200 million at the box office. If we look at the second, these are called bins or classes or buckets. A lot of terminology here, but one of the brackets here. The second one says that about, I'd guess around 1819, let's say 18 movies earned between 200 million and 400 million at the box office. And generally for histograms, the right endpoint does not count in this box. So if a movie happened to make exactly $400 million, they would go in the box to the right, or the bin to the right. But again, how you read this is, okay, $200 and $400 million. This bin right here, this interval, it corresponds to about 18 movies in 2011 made between $200 and $400 million. All right, a couple other things to point out with a histogram. The bars should all be touching. Notice they're touching right here, except in cases where there's nothing. So no movies in 2011 made between 800 million and 1 billion. But there are some movies here, those outliers from the previous, that did make over a billion in the worldwide box office. But otherwise, the graph should be touching. The y-axis is always going to be either frequency or proportion. So here we're seeing frequency, the total number in each bin. But sometimes you will see histograms with these being percentages or decimals, the percent of the movies or percent of the cases in each bin. And then lastly, the x-axis, I think kind of makes sense. If you go back to an algebra class, we have a solid 0. There could be negatives, if that makes sense, given the data set. For box office, there's no negatives, so 0, and then as far as you need to go. The x-axis is a number line. Okay, quick question. If you're given this picture without any other information, is this a histogram or a bar chart? Hopefully you guess histogram, because like the previous one, all the bars are touching each other, and the x-axis has numerical values. And this actually is the Rotten Tomato score for the movies in 2011. So if we're reading this graphic, I think I want to pick something. This is 10, frequency of 10. That corresponds, I think, directly with this bin right here I'm highlighting. So we would say you would read this graph by saying about 10 movies in 2011 had an audience Rotten Tomato score of between 60 and 70%. 60 and 70% audience Rotten Tomato score, about 10 movies in 2011. All right, is this a histogram or bar chart? Hopefully, especially after the last one, you see that this is a bar chart. Notice we still have bars, but the x-axis is no longer numbers, because bar charts are set up for categorical variables, or instead of numbers or categories. The height here is still frequency, so we're still given frequency of the movies, mostly action movies, animation, comedy, and so on. But the way the x-axis is set up for this is alphabetical order on the categories, A all the way to T. But those could be rearranged. You don't have to alphabetical order. You could do reverse alphabetical order. So you could rearrange these rectangles. As long as you keep the category set, it would still show the same information. Whereas on a histogram, we can't just rearrange these rectangles. Right? These numbers are very important on the x-axis. All right, just as a quick summary, a bar chart is for categorical variables, and the x-axis has no numeric scale. But for histogram, this is for quantitative numerical data, and the x-axis is numerical. It gives us numbers. For categorical variable, the number of bars equals the number of categories, and the number of each category is fixed. Whereas in a histogram, which is for quantitative variables, the number of bars in a histogram is up to you or the software. And the appearance could actually differ quite a bit depending on the number of bars you choose. So I want to go over a quick example of when that could happen. So I'm looking at stat key. Oh, sorry, this is cut off the screen. So let me see if I can make this a little better for you guys to see. Apologies, a little technical difficulty. Okay, so I want to do an example of making a histogram. So I'm going to go to one quantitative variable. And I'm going to click on histogram as an option. And this data is showing mammal longevity. There's a sample of 40 mammal species, and this is showing their longevity. So right here, you'd read about 3 species in this sample live between about 0 and 5 years. And if you click on show data table, okay, there's beaver lives 5 years, guinea pig lives 4 years, mouse and a possum. And don't forget, those 5 years will be in the next category. So there's the 3 frequency. And then we have one, I'd say maybe a little bit of an outlier that lives between 36. Oh, here we go. Highlight it. 36 and 40 years. And I think that's an elephant. Yeah, elephants live 40 years. So they're the outlier on this list. But I wanted to show you the number of buckets is 10. And with Stat Keys software, you just click and drag. If you want to make less buckets, 9 buckets, 8 buckets, notice the interval on the x-axis is changing as I do this. So now instead of 0 to 5, this is now 0 to 6.6 if you look on the right side of the screen. And at some point, if you want to be silly, we can go to 1 bucket. Okay, this is not very interesting. This is saying 40 animals are between 0 and 40 years lifespan. On the flip side, if you go show too many, actually if I'll go all the way to 40, each bar represents 1 animal because there's 40 animals in the sample, and that's not really condensing your information. So generally, as a general rule of thumb, histograms should have about 10 buckets. Somewhere around 10. 10 is not the magic number, 8 to 12, 7 to 13, but you don't want to go too less than 10 or a lot more than 10 to show your information in a concise way. So general rule of thumb, keep the number of buckets around 10 when creating a histogram. All right, okay, let's look at some shapes of histograms. Here we got information. This was data I gathered from students in semesters past. How much they sleep per night. This is self-reported data. How much they exercise in a week. How many hours they exercise in a week. How many hours they sleep in a night. And I asked their GPA. I think this is about 60 students. It was from 2 stats classes I had about a year ago. Anyway, we're just looking at these histogram distributions. Again, how we read this histogram is, sadly, looks like about 18, a little less than 20, 18 students got between 2 and 4 hours of sleep. And on the flip side of that, about maybe 10 or less students from the scaling got between 10 and 12 hours of sleep. But if you see a histogram like this, we would say the shape of this is fairly symmetric. I think if you were to draw a curve over it, it would be fairly even. It's not perfectly symmetric. There's a little bit more on the left side, but it's a fairly symmetric distribution. Compared to exercise, here most people in this survey did, I would say, less than 6 hours of exercise a week. But then I had a couple student athletes, whether it's practice or a couple people just like exercise, were getting, 20 plus hours of exercise a week, or 15 to 20 hours, a couple right here. So when you have a shape like this, where a bulk is on the left, but we're going to say the tail goes towards the right. Imagine drawing a curve on top of the histogram. We're going to say that's right skewed, or skewed to the right. So right skewed means the tail goes towards the right. And if we look at the GPA, bulk of the GPAs were pretty high. That's a good sign. So 3 and higher. But here, if we were to draw a curve, I wouldn't say that's symmetric. It's definitely not right. We would say this is left skewed. So right skewed for exercise, left skewed for GPA. I would add some terminology and say that this is very strongly right skewed. There's a strong or long right tail, and this is a weaker left skew. There is a statistical measure for skewness called kurtosis, and we're not going to cover that in this class. We're really just going to look at kind of visualizing histograms and dot plots and box plots to get skewness. All right, so let's look at one more example on this video. These are 2 examples of distributions, histogram distributions that are called bell-shaped. So we're going to say a histogram is bell-shaped if it's 2 things. It needs to be symmetric. Both of these are fairly symmetric. There's not a strong, long tail on either side. And I'm going to say unimodal. So bell-shaped means symmetric and unimodal. Actually, I want to put that down here just to connect that with this. We say a distribution is bell-shaped if it's symmetric and unimodal, meaning just one hump in the middle, bell-shaped and unimodal like this right here. All right, we'll continue in the next video.